The professor is Marta Lewicka from the math department in the University of Pittsburgh. So she will talk about calculus of variations.
Thank you very much for the invitation, for your interest. So this will be a series, short series of talks on the mathematics of morphogenesis which means shape formation. And this will be, the lectures will be given from the point of view of mathematician, analyst. I am an analyst specializing in partial differential equations, calculus of variations, also some aspects of Riemannian geometry. And indeed, in the lectures, we will see how many concepts, ideas from different fields of mathematics combine and give us a better, hopefully, understanding, precise mathematical understanding of shape formation. So in my talks, we will see concepts from the following fields of mathematics: calculus variations, Riemannian geometry, and nonlinear elasticity, mathematical nonlinear elasticity. So in calculus of variations, we will in particular define and understand properties of an energy functional will be called capital E for elastic materials with residual stress at free equilibria. We will perform what is called a dimension reduction for this type of energies. This energy functional is actually non-convex. Dimension reduction and the dimension reduction will be done by means of technique that's called gamma convergence, which is the primary type of convergence in calculus of variation. Okay, so I'm just giving you the list of topics, and hopefully you will know that after my lectures, you will know the definitions of those concepts and will be able to somewhat, prove some results using this. So this is for the calculus of variations. For Riemannian geometry, you will see that that energy functional E actually measures the deviation from isometric immersion. The deviation from isometric immersions. We will develop the scaling laws for the infimum of this non-Euclidean elastic energy. And we will see how those scaling laws are related, so scaling laws in relation to the Riemannian curvatures. Okay, Riemannian curvatures of a Riemannian metric, which defines the pre-strain imposed on the referential configuration of a given material. We will observe curvature constraints. And in particular, they will lead to the Monge-Ampère equation. And Monge-Ampère system in the prescription of the curvatures of a shallow manifold. And then finally, in nonlinear, okay, so this is for this is for this, and in nonlinear elasticity, we will see how this E reduces to versions of the Kirchhoff, von Karman, and linear elastic energies in the context of restrained materials. So something old and something new. So basically, I will be reviewing the mathematical results in this, in the context I have proposed here, and I will be also listing open problems. So let us start. The departing point of view that I will adopt is that shape formation is determined by the local metric imposed on the referential configurations. Imposed on the referential configuration. Okay, so omega will be a subset of R3. In general, it's an open, bounded domain. And on this omega, we are given G. So let me actually note it by little g. Given G, that is a Riemannian metric. Okay, so if you don't know what a Riemannian metric is, that's just a very simple mathematical object. You will think that it's a C infinity. I will always discuss only smooth case. It's a C infinity map on omega, I'll say omega bounded, with values in the space of R 3 by 3 symmetric matrices, okay, 3 by 3 symmetric matrices that are positive definite. This means symmetric positive definite. So given omega, given G, like this, G belongs to this, we look for deformation, which is a map U that goes from omega to R3, which has certain regularity, we'll discuss later, such that gradient U, okay, so gradient U, this is a matrix which carries all partial derivatives, all components of U. So it's a 3 by 3 matrix. Transpose times itself equals to G. This in coordinates, it means that, I mean, this is already written in coordinates, right? So this should be true in valid the whole omega. So this means that DIU, scalar product, that's a vector, of DJU equals to GIJ for every IJ from 1 to 3. Okay, so we want to find the deformation in general, which immerses a prescribed, isometrically immerses a prescribed metric that is given on omega. Okay, now remark 1. In general, this system of PDEs, okay, so here I have a particular, I mean the equidimensional case. So U goes from 3 dimensions to 3 dimensions. In general, I can study the system gradient U, transpose gradient U equals G, where G is given on omega, which is D-dimensional domain. Okay, so here for us D is 3. who are d by d symmetric, positive, definite. And I'm looking for u, which goes from omega, again, omega is d-dimensional, to d plus k dimensions. Okay, so I will have d dimensions and k codimension here. Okay, so in general, I can study this problem. This is called the system of isometric immersion. System of isometric immersion, and this is a particular system in the equidimensional case, okay, where d is 3 and k is 0. So it turns out that studying existence of solutions, regularity, and dimensionality has been a very interesting, very important direction of research that's quite vibrant and fruitful up to this day. So we want to exclude, so remark 2, or rather I will put it here. So this is my problem, and I want to preserve the orientation. So preserving the orientation means that the determinant of gradient u is positive, okay, in omega. Here in capital omega. Okay, so I want to find an isometric immersion which preserves the orientation. Okay, on omega. So remark 2, let us see what this full mathematical statement means in the simplest possible case, that is when G is identity. So if G is just an identity, 3 by 3 identity metric, then the problem becomes to look at gradient U transpose gradient U equals identity. And you want that determinant gradient U is positive. Okay? So the fact that gradient U transpose gradient U is identity, this is equivalent. It just says that gradient U belongs to the orthogonal group, belongs to O of 3 for every x, right? So what is O of 3? This is just exactly the set of, right? So the set of F 3 by 3 matrices, okay? Such that F transpose F equals to identity. Okay, so not without that, just this is equivalent to this. And O of 3, in fact, O of n, or any n, has two connected components. Okay, so O of 3 is the union of SO3. This is a connected compact manifold, which consists of those members of O of 3 that have positive determinant. So automatically the determinant has to be equal to 1, right? Determinant of this times determinant of this will be equal to determinant of this is 1. So the solution is either determinant of gradient U is 1 or minus 1. Okay? So being in O of 3 means that either I am in SO3 or I am in the other connected component, JSO3. So JSO3 means that I'm taking this orientation preserving rotations and I am multiplying by the matrix J, which is just minus 1, 1, 1. Okay? So in SO3, I have positive determinant, and here I have determinant equal negative 1. So solving the full problem that I'm proposing here, namely gradient U transpose gradient U equals identity, with the extra constraint that the determinant gradient is positive, which automatically means that the determinant of the gradient is 1, okay, means that I am looking for U whose gradient at every x belongs to just one of these two separate connected components, namely SO3. And it turns out, this is called Lewis theorem, Lewis theorem, that automatically such map must have a constant gradient. Okay, so Lewis theorem says that if you, with some regularity, let me write W1, which essentially effectively means here W1 infinity on omega to R3, satisfies gradient U belongs to SO3, okay, for almost every X in omega, then gradient U is constant. It's a constant rotation. Right? So, i.e., U is a rigid motion. U of X equals some Rx plus B for some R in SO3 and B in R3. So this type of result is that we will see many results of this flavor in my talks. This is the first installment of what we call a rigidity theorem. Rigidity theorem means that if I have a certain constraint, okay, this constraint here, then the behavior of the map which satisfies this constraint is rigid. Okay, I have just basically I have one, up to rigid motions. I have just one solution. It's smooth automatically. It's prescribed in this manner. Okay, so let's prove it. Prove. So we are going to use the following identity. Divergence of a cofactor of a gradient is always 0. Okay, this is a homework. So let me remind you what is what here. So if I have a matrix F, here in general, right, the D by D matrix. Here we are in the 3 by 3 context. If I have a matrix, then what is the cofactor matrix? So cofactor matrix consists of components. That's exactly what you calculate when you calculate the inverse of a matrix. Okay, the cofactor of F, its ij component is you take the determinant and you take F and you remove the I row and you remove the j column. Okay, removed. Then you get a D minus 1 by D minus 1 matrix, and you take the determinant of that. And you multiply by minus 1 to power I plus j. Okay, that's exactly what you compute when you compute the inverse matrix. So, right, so when F invertible, then F minus 1 is 1 over determinant F times exactly the cofactor you have to transpose. So in the case when F is invertible, right, you can compute it for any F, but when F is invertible, then the cofactor F is determinant F, that's just a scalar factor, times F inverse transpose. Okay, and here the mathematical statement, just you have to sit and calculate, or you can ask me, is that if you have a gradient, okay, matrix field, you take its cofactor, this is defined in this manner. So this is a matrix field. Then the divergence of a matrix is computed row-wise, right? When I write the divergence, I take divergence of each row, the first row, the second row, and so on. This gives me a vector field. So divergence of a cofactor gradient is always 0. A very useful identity. So now let's use it here. First part of the proof. So let's take a gradient about whom I know that it's in SO3. And let's compute the divergence of its cofactor. So gradient U is in SO3. Of course, it's invertible. So I claim that the cofactor gradient equals to the gradient, right? And it's clear from the definition because, right, so determinant of this gradient is 1 because it belongs to SO3. And if it's in SO3, then the inverse and transpose cancel. So I get exactly the same thing. So this is divergence of a gradient, right? So using the fact that gradient U is in SO3, this is the gradient itself. So I get that the Laplacian U is 0. So my function U, right, for which I assumed only that almost everywhere pointwise its gradient satisfies this constraint, automatically has to be harmonic. So in particular, from this it follows that U is smooth. So I can take as many derivatives in a strong sense as I want. Okay? It's a harmonic function, just a measurable function that's harmonic in the sense of distributions, automatically is smooth. Okay. So let me look at the length of the gradient. It was step 2, now step 3. So what's the length of the gradient square? The gradient is in SON, it's in SO3 here. So the length of the gradient is constant, right? It's the same as the length of identity, which is square root 3. And I'm going to take the Laplacian of this. So because this is constant, Laplacian of this is 0. So Laplacian is divergence of the gradient. And let me just rewrite it. That's, so what's the length square? So there's the scalar product of the gradient against itself. Okay, just the gradient length square. So here I have two derivatives, right? So if I put two derivatives on a product, I have two possibilities. Either both of them fall on one of these components, or one falls on this and the other one falls on this. Okay, so I have two terms when I expand it, and both of them, so this is Laplacian, fall on just here or here. I will have twice Laplacian gradient U against gradient U. But, well, U was harmonic, right? Laplacian U is 0. So Laplacian gradient U is also 0 because partial derivatives commute. So that is 0. And the second term comes from putting one derivative on this and one derivative on this. So this will be length of the second derivatives, table of all second derivatives of that field, square. Okay, so I discover, so this is 0, so this is finally just twice length Hessian U square. So I discovered that the Hessian U is 0. Right? Hessian U being 0 on a, so let's say on a connected domain. So this is my U from the very beginning. Let omega be open bounded, also connect. Right? So if Hessian, which is the gradient of the gradient, is constant, is 0, means that gradient is constant. So we prove the result. Okay, so again, what the Lewis theorem says, it says that if you have your deformation U, right, and locally you see at each x, it is a rigid motion, positive orientation, right? It's a rotation and a translation for almost every x, then it means it must be a global single rotation and translation. So remark 2, what did I have? No, remark 3. This is a rigidity theorem, rigidity statement. So now I have a quantitative version of the statement. Rigidity inequality. And that's a beautiful, very important and groundbreaking result due to Lewicka, James, and Mueller. So it's the following theorem. So if U is, say, W12 from omega to R3, then there exists a single rotation in SO3 such that the integral of gradient U minus R squared dx is bounded by a constant which depends only on the domain times the integral on omega distance square of gradient U from SO3 dx. Okay, so let's unpack it. So in particular, that's a quantitative version of the Liouville theorem, because if the right-hand side is 0, right, what does it mean that the right-hand side is 0? It means that gradient U, or this is a non-negative integrand here, right? So this means that this integrand, this function is 0 for almost every x. So this means that gradient U for almost every x is in SO3. This means that the right-hand side is 0. So this means that the left-hand side is 0, namely gradient U is that single rotation, which I found here. So in particular from this, I recover Liouville theorem, but I have more, right? I know that even if that is not 0, then still I can see it as an error from gradient U being a constant rotation. There exists a constant rotation such that this is the deviation from gradient U being a rigid motion with that constant rotation as its gradient. So this theorem is very important and allowed for carrying out the dimension reduction in nonlinear elasticity. This theorem is also a nonlinear version of Korn's inequality. Korn's inequality is important in the linearized, in particular, the linearized linear elasticity. Okay, so let me comment on that. Let me comment why this is a nonlinear version of Korn's inequality. So what is Korn? Korn's inequality. So Korn's inequality says that if V is again, let me write W12 from omega to R3. So we think about this U as a deformation. Now you should think that this V is a displacement. I will draw the connection. So the theorem is if V is like this, then there exists a constant skew symmetric matrix. So A, which belongs to little SO3. Okay, so what is, so big SO3 I defined, little SO3, so these are all matrices which are 3 by 3 here, such that A transpose equals negative A. Okay, skew symmetric, little SO3. So for every V, there exists a constant skew symmetric matrix such that gradient V differs from that A by means again of a constant, which is a scaling factor, which depends only on omega, integral on omega, symmetric part of the gradient V square. Okay, so what's the relation of this to this? First of all, to put it in a somewhat similar write-up, observe that symmetric part of the gradient, the length of it is exactly the distance of the matrix at hand, here gradient V of X, from the space of skew-symmetric matrices. Okay, so that's exactly the distance. So this thing square is the distance square of gradient V from little s of 3. Because, so this is the picture in R3 by 3, I have here little s of 3, and I have skew-symmetric matrices, and then I have symmetric matrices, and they are orthogonal. So every matrix can be written as a sum of its symmetric and its skew-symmetric component, and every symmetric matrix is orthogonal to a skew-symmetric matrix, right? That's obvious statements. So if I have gradient V sitting, gradient V of X sitting somewhere here, then its distance from skew is exactly given by the length of its symmetric component. Okay, and I have a square here. So this statement looks pretty similar to this statement, right? So I have this functional kernel, the distance from the pointwise distance from the kernel on the right-hand side, and in the left-hand side, I have a distance from the functional kernel. So the relation, that the reason why this is the nonlinear version of Korn's inequality follows from the fact that if I look at SON, SO3 in our discussion, identity is sitting in it, right? Then the tangent space to identity, tangent space at SO3 at identity consists exactly of skew-symmetric matrices. Okay, so this is the tangent space at three-dimensional identity to big SO3. And this equals to little SO3. This is little SO3. The linearized rigid motions, these are true rigid motions. Okay? So if I take a deformation whose gradient, let's say, is close to identity, so if I take, under making an ansatz, that gradient, that U is, okay, so U is identity plus V, and let's say this is small displacement. This is a deformation. So that gradient U is identity matrix plus gradient V, which is small, right? I'm just making heuristics here. So I have gradient U sitting somewhere here close to identity. Okay. Then its distance from big SO3, right? Distance from big SO3 is basically the distance from the tangent plane to identity up to higher order errors. Okay, so that's the distance. So distance of gradient U from big SO3 is like the distance of gradient U from the tangent plane. Okay? What's the tangent plane here? That's identity plus the tangent space. So plus SO3. Okay? So this equals the distance of gradient U minus identity from little SO3. But that's the gradient of your displacement. And the distance of gradient V from SO3 is exactly the symmetric part of the gradient, length of it. If I'm thinking about small displacements, then up to the leading order term, and this is in fact how the proof of, how the proof of this goes, is, right? So here, I basically get this. And distance of the full gradient from a one fixed rotation is approximated like by the distance of the displacement from the linearized rotation, which is a skew-symmetric, constant skew-symmetric matrix. Okay, very well. So now we go back to our original discussion. So this is we want to find a deformation U, which preserves the orientation and which immerses a metric. And we've seen what happens in a particularly simple case with the discussion here when the metric is identical. So in the general case, I'm going to write, so we have this gradient, right? So gradient Q transpose gradient Q equals to G, and I want to keep the determinant gradient Q positive. So by polar decomposition theorem, this means that gradient Q is a rotation times a symmetric matrix, of course, because it's orientation preserving, the rotation has to be, it's a rotation, right? The determinant is 1. So it's some R in SO3 times the symmetric part of the symmetric component of this is the square root of gradient Q transpose gradient Q, right? That's just polar decomposition theorem, but that was called G. So it's R times G to 1/2, like square root of G. So in fact, what we've done here is that this statement is equivalent, right? So we've seen this is equivalent to gradient U at each X being a rotation times the square root of the matrix, of my metric. So this means that gradient Q times G inverse 1/2 belongs to SO3. Or let's say almost every X, Okay, so in this direction, just polar decomposition theorem. In the other direction, there is nothing to prove, right? If I have gradient U being some rotation G 1/2, then gradient U transpose is that G 1/2 times R transpose R times G 1/2, and R transpose R is identical. So G 1/2 times G 1/2, which is G. So we have the following next remark, I guess remark 4. So if U, say Lipschitz, satisfies the above, then U must be smooth. And it's the same proof that we've done for G being equal to identity. Okay, that's why I presented it first. So let's now see this proof. This is because, again, I'm going to use the fact that divergence of cofactor gradient is 0. Okay. So what's the cofactor of the gradient? So my gradient is some rotations times G 1/2. Okay, so this is, so now I'm writing this is cofactor of, right, this gradient is R G 1/2. So of course it's invertible, right, clearly. It's a product of two invertible matrices. So the cofactor, Okay, so the cofactor is given by the formula that we've seen before. This will be the determinant. So let me maybe write it here, right? So what's this cofactor? So this will be the determinant of Rg1 half times Rg1 half transpose inverse. So of course, determinant of R is 1, and determinant of G1 half is the square root of the determinant G. I have here product of those two matrices. I have the operation which is transpose and then inverse. Both of them shift the order of matrices, but I have two of them, so the order remains the same. So I have R transpose inverse times G 1 half transpose inverse. So that is square root determinant G times R transpose inverse is the same R. And G1 half transpose nothing because it's a symmetric matrix inverse. This is G inverse 1 half. Right? And in fact, R G inverse 1 half is almost gradient U, because gradient U is R G1 half. Okay? So I can write it as determinant G, just copying, times R G1 half is gradient. And then I have to put here G inverse, right? Because here I am including G 1 half times G inverse 1 half. So this R G1 half is gradient U, and then G minus 1 half, G minus 1 half is G minus 1. Okay, so that's the formula for the cofactor R G1 half, cofactor gradient. Of course, if G is identity, then this is 1, and this is still identity. So we recover the previous formula that if gradient, right, if G is identity, then the cofactor gradient is equals to the gradient itself, which led to the fact that divergence of the gradient was Laplacian. Laplacian was 0, so U was the harmonic function. Okay, so here I have a divergence of this, and that's also a Laplacian. It's a so-called Laplace. It's almost up to a numerical prefactor. It's a Laplace-Beltrami operator with respect to that metric G of U. Okay, so the prefactor, so I would have to divide by square root G. So this is square root determinant G times the Laplace-Beltrami operator of U. And again, because this is 0, okay, I have ellipticity statement. This is 0. So this means that U is smooth. Okay, so this constraint, if satisfied almost everywhere, means that actually it's satisfied everywhere, and U is a smooth function. And we have the following theorem, which is the counterpart of Liouville's theorem. It's not, well, exactly Liouville, it's not exactly rigidity theorem, but it has this flavor in the context of an arbitrary Riemannian metric, equidimensional isometric immersion thereof. So it says that if U Lipschitz satisfies gradient U transpose gradient U equals G, and determinant gradient U positive for almost every X in omega, then that's what we check. U is harmonic with respect to the Laplace-Beltrami operator given by the metric G. Use little g here, sorry. Little g. And so U is smooth. And in fact, unique. I'm not proving this statement, right? But we checked the uniqueness up to rigid motions in case of identity. Otherwise, it's a more complex calculation that I'm not going to look at. In fact, unique up to rigid motion. Moreover, such U exists, right? So such U, namely the solution of this problem, exists locally if and only if the Riemann, all the Riemannian curvatures, the Riemann curvature tensor of G is equivalently equal to 0 in omega. So what's the Riemann curvature tensor here? Okay, so that's for three-dimensional situation. These are six equations involving second-order derivatives of G. There are some complicated formulas, but if you want to know whether your metric is immersible in the equidimensional case, okay, so your metric is, say, three-dimensional, and you want to understand if it has an isometric immersion in R3, then an if and only if condition that this happens is that, in that case, those six equations, okay, we have six Riemann curvatures, but they are equivalent to Ricci curvatures because of the symmetry. All curvatures have to be 0. And if that is true, then locally the isometric immersion orientation preserving exists. And in fact, it's unique, it's automatically smooth. And in fact, it's unique up to rigid motion. So this case should be confronted.
Excuse me, I have a question.
Yes.
Because there is a if at the top and the if and only if at the bottom.
So there are two statements. So this theorem consists of two parts.
Yes.
First part is this, and this is the second part. Right? So the first says that if I just have a Lipschitz map, which solves that, then in fact, automatically it must be smooth.
Yes.
Okay? It's harmonic with respect to this Laplace-Beltrami operator. Yes. Automatically it's smooth, and it must be unique up to rigid motion. So I cannot have two solutions. If they have two solutions, then they are just one is given by the first solution, composed with some rigid motion, that's rotation and translation. Okay, so it's the first part of the theorem. And the second part of the theorem, that's why I write moreover, but it's the second part, says that U, such U, meaning a solution to this, right, exists if and only if I have that. Okay? So this orientation preservation condition is crucial here. Because I have the following theorem. So this is another rigidity statement, another whole thing, rigidity theorem. This is the first rigidity theorem was the Lewis theorem when G was identity, and then I automatically knew that the only isometric immersion is a rigid motion. Of course, it exists. I mean, all the second derivatives, all the derivatives of identity are 0. So the Riemann curvature of identity is 0. Okay, so the second, this moreover condition is involved here. Okay. So if I forsake this condition, orientation preservation, if I only think about solutions to that, okay, that is if I allow, in the case when G is identity, to jump between those two connected components of O of 3. Then, in fact, not only the isometric immersion is not unique, not only it may not exist. It always exists. It's not unique, and the set of such isometries is very large. Right? Theorem, let U0, let's say 1 from omega to R3 be such that satisfy gradient U0, transpose gradient U0, positive definite, and this negative definite with respect to G in omega. Okay, so what does it mean? This means pointwise in the sense of matrix inequalities. So this is negative definite with respect to that, right? So G minus this is a positive definite 3×3 matrix. And it's likewise here, this means it's an immersion in the sense of matrix inequalities. Okay, so I take a U0, such U0 is called IE, it's just the language definition, such U0 is called a short immersion. The 0 is a short immersion. Okay, so short immersion means that just I decrease the distances instead of realizing the distances perfectly, the distances given by the metric G. Then, for every epsilon greater than 0, there exists U, okay, which is W1 infinity from omega to R3, Lipschitz, such that U minus U0 in C0 norm is less than epsilon. So U is close to that prescribed U0. And gradient U transpose gradient U is G. Okay, so how does this statement differ from the statements that we've been discussing before? It just differs by the fact that I'm not requiring the positiveness of the orientation. I'm not requiring this physical relevance, if you want. Okay, determinant gradient. So if G is identity, I'm taking any U0 short immersion. So you can take any immersion and multiply it by a very small number. Okay, then of course, this is going to be negative definite with respect to G that is prescribed, that is given. And then I say that such U0, no matter what it was, you see, it has no geometrical connection to G, apart from this inequality condition, shortness condition. This U0 can be approximated with as small error as you want by a Lipschitz W1 infinity exact isometry. So if G is identity, it means that gradient U is going to jump, right? Gradient U can be both here and both here. It cannot be here all the time, because if it was here all the time, then my Lewis theorem, okay, it would mean that it's constant. Okay? Because a constant gradient linear map, this linear map cannot approximate U0. U0 is just anything. Think of U0, which is like a nonlinear function. Okay, so in fact, okay, so that's a theorem close to any x in omega, where the Riemann curvature of G at this x is not 0, gradient U, determinant gradient U, will change sign infinitely many times. So this type of theorem is called the flexibility theorem. Flexibility theorem. So you see here in this discussion, I have rigidity and flexibility, two completely opposite scenarios based on the satisfaction of the orientation preservation condition or the absence thereof. Okay. So that's really the starting point of our discussion. And now I introduce this key persona in my talks, which is the energy functional E that we want to discuss and study from the point of view of those three types of techniques in mathematical analysis. So being orientation preserving isometric immersion means that gradient U G inverse is in SO3, okay, for almost every X. So maybe it's good to actually do it here. So I define E of U for every U, which says, say, W12 from omega to R3 as an integral over omega. So let's call it D0, distance square of gradient U from SO3. Okay. We have observed that E0 of U equals 0 if and only if, right? Sorry, so I want G. G inverse 1/2, the distance from SO3. Okay, so this is in SO3, if and only if I have this orientation preserving isometric immersion. So that is 0 if and only if U is an orientation preserving isometric immersion of G. Thus, by what we stated, automatically smooth, unique up to rigid motions, and it basically never exists, right? It only exists if G is flat. That is when the Riemann curvature of G is 0. So in practice, we will study E of U as, instead of this distance square, I will take a general energy density, elastic energy density, that's computed on gradient U, G inverse 1/2, okay, where W, that's a map from 3×3 to R, positive, possibly infinity, satisfies. So this is an elastic energy density. It satisfies the following conditions. First, W on any rotation times F is W of F, prime invariance, for every F in R 3×3, and for every R, which is in SO3. Okay, prime invariance. Then I want that W at identity, and therefore at any rotation, so W restricted to SO3. So on SO3 is just 0. Okay, so the energy of a rigid motion is 0. Nothing happens, just rotation and translation. Further, I want this non-interpenetration of the matter. So so W of F goes to infinity when determinant F goes to 0. So if I'm squeezing infinity, that it costs me infinite energy. And W of F is infinity for determinant F negative. Sorry, and finally, you see, this condition says that W is minimized at SO3. Okay. So it means that its first derivative, the first derivative of W on SO3 is 0. So my second condition is that I don't want that my second derivative of W is 0. So I want that W departs quadratically from SO3. And this is delivered by assuming that W of F is greater than there exists some positive constant, such that W is greater than this constant times distance square of F of the argument from SO3. Okay, so I have this SO3 here. On SO3, my W is 0, right? Because it is 0. This is what's written here, but also it's minimized on SO3. So I want that from SO3 it departs quadratic. Right? It departs quadratic. I have this lower bound. So a prototypical mathematical example of the energy E is this one, where W is just a distance square of its argument from SO3. But I can, so everything that all the discussions we will be carrying through will be, for arbitrary W will be valid for arbitrary W which satisfies this property. So what I want to do is I want to understand what can I say about the minima if they exist, or infima of those energies. We want to understand the infimum of E of U over U, which are vector fields from omega to R3. Okay, so what is this? And naturally, it should depend on the measure of non-immersability of G, right? On the curvatures of G. We checked here that the energy is 0 if and only if G is flat and possesses then automatically smooth isometric unique after rigid motions isometric immersion, and then only on that isometric immersion the energy is 0. Okay, the same here. So the first statement, my theorem, that I want to propose here is that, in fact, minimizing, so the infimum, this infimum of E is 0, if and only if the minimum of E is 0. So that's the first condition, and I say it's equivalent, perfectly equivalent to the second condition when I say the minimum of E is 0. Okay, but I know that minimum of E is 0 means that, okay, so minimum is 0, i.e. the Riemann curvature of G is 0, and the minimizer, so argmin of E is an isometric immersion, orientation PZ. Okay, according to that discussion. I want to give you a sketch of proof of this theorem, but first a remark. Next, I think we were at 4, so maybe remark 5. So what does this mean? What does this statement mean? Okay, so this means there is an energetical barrier. Dichotomy. So either G is flat, so the Riemann curvature of G is equivalently equal to 0, which means the situation is completely trivial, right? So this is 0, so there exists a solution to our problem with the terminal gradient U being positive and minimum E is actually 0 and argmin of E consists of U's like that. Or if that is not the case, that is, if you cannot, by means of one single smooth change of variable, make the whole situation completely trivial, the infimum of the energy is strictly positive. So there exists an energetical barrier. So this is sort of striking if you haven't seen it before, because you might say, okay, maybe there is no one single smooth, right, unique up to rigid motions, isometric immersion of G, but maybe sort of locally I can put some origami construction, some structure which brings the energy as low as I want. Okay, this energy. Maybe I can locally introduce some jumps between, you don't have orientation preservation per se condition. Of course, it's sort of included in the statement that that's the distance from SO3, but it's not given explicitly here. So maybe you could introduce small length scale oscillations, corrugation, spirals, and bring the energy very close to 0. No, you cannot. So either by means of one single automatically smooth, trivial, which almost never exists, change of variable, you bring yourself to 0, or there exists a positive energetical barrier that you can never pass. Okay, so now the proof, sketch of proof of theorem. So I'm going to check, of course, that the condition 1 implies condition 2, right? 2 implies 1 is 3. So assume, first step, maybe not, assume that infimum is 0, so I have a sequence such that E of UN converges to 0 for some sequence UN W12 from omega to R3. Okay, so that's a sequence from n equal 1 to infinity. I have a minima infimizing sequence. Okay, so this means in particular, that's just a comment here. If you look at this energy, right, it measures the distance of gradient U from SO3 modulo this G. Of course, G is all bounded, right? It's a matrix, its inverse is bounded, itself is bounded. SO3 is compact, it's also bounded. So in particular, it means that gradient U square is bounded. Okay? So this means in particular that gradient UN in L2 is bounded by universal constant. So up to a subsequence, and possibly modifying by a translation to get the bound in W12, not just in L2, we get UN converges weakly in W12 to something. And you see the weak convergence, right, which is the weak convergence of the gradients, is not enough to pass to the limit in U. I know that E of UN, which is this, so okay, think about this, goes to 0. So gradient UNs converge only weakly to some gradient U. It's not enough to conclude, okay, that this converges to the E of U in general. But I'm going to check that in that situation, that's the essence of the proof, that is actually true. So we have this compensated convergence statement. In fact, we will show that UN converges strongly in W12 to U. And that's only due to the fact that those energies converge to 0. I don't claim that infimizing sequence of the energy in the non-Euclidean case, that is when I have this energetical barrier, equals to the minimum. That's an open problem, okay? We don't know it. But if the energy goes to 0, if the infimum is 0, okay, then in fact, the infimum equals to the minimum. And we are going to find the minimum, therefore, I will get 2, okay, as a limit, strong limit of those UN. And I have to prove that's a strong limit. Okay, so the first step is, okay, that's not, I'm not going to, I don't have time to discuss it, is that you can, without loss of generality, assume that those UNs are not only bounded, their gradients are not only bounded in L2, but in fact, their gradients are bounded uniformly. They are bounded in infinity. So by truncation theorems, it follows that it suffices to show, well, let's say this is star, okay, to show star, under assumption that gradient UNs in L infinity are bounded by one fixed constant. Okay, again, there is no reason to that is satisfied for an arbitrary infimizing sequence, but I claim there is a method of truncating that infimizing sequence to obtain another infimizing sequence, okay, such that I also have this, but with the extra property that gradients at each, for every n and for every x, the gradient sits in one fixed ball in the 3x3 matrix space. Okay, so that's step 1. In step 2, we are going to use this harmonic plus non-harmonic corrector decomposition. In this type of rigidity statements, effectively, that's another rigidity statement, is very useful and is used in many different proofs of this type. So we will decompose. We will write each UN as Wn plus Zn, and Wn is harmonic, and that's a corrector with 0 boundary condition. So harmonic, of course, harmonic with respect to the Laplace-Beltrami operator, with the G Laplacian related to symmetric G, right, that we discussed before. So what do I have? I have Wn, I have Zn, so I have G of Wn will be 0 in omega, and Wn will be equal to Un on the boundary of omega. And G Laplacian of Zn will be G Laplacian of Un, right? If the sum is Un, if the Laplacian of this is 0, so the Laplacian of this must be equal to the Laplacian of this. And Zn equals 0 on boundary omega. Okay, I can always do it. I just solve this problem. And then I declare Zn the difference of Un and Wn. Okay. So I'm going now to take this and integrate by parts against Zn using the fact that Zn is 0 on the bound. Okay. So you remember that that was the divergence of the gradient, right? So if I multiply this by Zn, I can put this divergence on Zn, it becomes the gradient because there is 0 boundary condition, so there is no boundary terms. So I obtain square root determinant G times the scalar product of gradient Zn times G inverse 1/2. Right, so maybe let me write first. So what am I doing? I'm taking, I'm looking at Laplacian, G Laplacian Zn against Zn, right? These are vector fields. And I'm taking the inverse. I'm taking the integral with, let's say, with minus sign of this on omega. And of course, this equals to integral of Laplacian of Un against Zn, right? Because this and this are the same. Dx. But now integrate by parts. That's why I put this minus here. So I will have determinant, right? So what was that? We know what like we had the formula. So that's determinant G square root. And now I have gradient Zn times G inverse against gradient Zn. Right? I put the divergence on Zn. This minus here. And the same thing I can do here, only that I get the integral on omega, determinant G 1/2, gradient Un now, G inverse against gradient Zn. Okay, so this equals to this. Now this thing is morally speaking up to a constant L2 norm of the gradient Zn, right? Because I have, these are all bounded from above and below, all coefficients. So this thing is greater equal than some constant times the integral length of Zn squared. Okay, L2 norm of gradient Zn squared. Now, what can I say? What am I going to do? I'm going to massage this a little bit. So I claim that now for free, I can subtract the scalar product of cofactor gradient Un against gradient Zn, right, under the integral sign. So let's do another integral. Why? Well, because if I integrated by parts backwards, I would have divergence cofactor gradient Un against Zn 0 on the boundary, so no boundary terms, and divergence cofactor gradient is always 0. Okay, so that term is actually 0. Just for free, I subtract. Why not? So this means I have gradient Zn here, gradient Zn against this minus this. I continue here. This is integral of determinant G 1/2 gradient Un G inverse minus cofactor gradient Un, whole thing against gradient Zn So by Cauchy-Schwarz inequality, this is bounded by L2 norm of this times L2 norm of this. Okay. We have 4 minutes, so let's conclude this. So now I claim that this is actually bounded by some universal constant times the energy of UN to power 1/2. Why? So what do I see here, right? This is then, so this is an integral on, okay, let's write a function, let's write f of gradient UN square, where this f of, okay, any matrix capital F, in particular here, this is gradient UN at a given x, right? This is the x. But this is, okay, determinant G to 1/2 at a given x. Okay, so this is f of, so this is, let's say, how should I put it? So f depends also on x, right? F super x. Fix your x. When you fix your x, then f at computed at that at x, of course, equals to this f times g of x inverse minus cofactor of f. So of course this, like for a fixed x, that's a smooth function of f, smooth matrix function. Right, clearly. So so maybe let's take the yeah, it's a smooth function, and f on what? So f on R G 1/2 of x is 0 for every R in S of 3. We checked it. This was the part of the proof before. Okay, if you check your notes. So we checked it that exactly if capital F is some rotation times square root of G, then this is 0 because cofactor of it, right? This was the formula that we developed. The cofactor of something like that, this was our assumption, assume that gradient U is R times this. And we checked that then cofactor of it equals to that. Okay, we checked it. So I can write that fx of, okay, of gradient U n minus fx of, okay, any rotation G 1/2 of x. This is exactly equal to fx of gradient Un, right? This is 0. But now it means that fx of this minus f of this, fx being a smooth function, is Lipschitz for matrices which are in a bounded set. But I know that all, you see, this is always this for any x, anyways, your x is fixed, right? So this is in some bounded set. And this is always in a bounded set because this is what we assume. This was the first part of the proof, right? By truncation theorems, I can assume that gradient Un always sits in a bounded set. So I know that this is C times gradient Un minus RG 1/2 of x. So this is C gradient Un G inverse 1/2 of x, right, bounded, minus R. And I see that indeed what I see here, the integral of that, I can do it for any rotation. So in particular, I can take the rotation, which is the closest rotation. Okay, so by just almost done, by taking the closest rotation in SO3, we get that this f of x of gradient un, length is bounded by universal constant, which only depends on that upper bound of the infinity norm of gradients, times the distance of gradient un g inverse 1/2 from SO3. So now the square of this is in L2 norm. I have integral of the square of this is bounded by the constant integral of the square of this. But that's exactly my energy. And of course, there is 1/2 because in L2 norm, I have integral to power 1/2. Okay, so almost done. So what follows is that constant integral gradient Zn, this was my corrector, square, is bounded, right? The chain of inequalities, then the L2 norm of the gradient Zn, so integral gradient Zn square to power 1/2 times the energy constant. So here I have the square of L2 norm. Here I have the L2 norm itself. So I can divide by it. Okay? From this, it follows that that gradient Zn L2 norm is bounded, okay, by E of un 1/2, but this goes to 0. So gradient Zn goes strongly to 0. Goes strongly to 0 in L2. But I knew that gradient un, original gradient un, written somewhere here, okay? Gradient, so uns converge weakly to u in W12. But un was Wn plus Zn. Now I know that Zn converges strongly to 0. So it means that in fact, Wn's themselves, the harmonic Wn's, converge weakly to that u, that's the limit of un. Okay? So UNs converge weakly in W12 to my limiting U. But those, sorry, WNs, right? That's the whole point. But those guys are harmonic. So I have elliptic estimates, I have a lot of regularity, classical regularity theorem tells me that if I have harmonic functions which converge weakly in W12, okay, then in fact, they have to converge strongly in W12 log. Okay? So this means that gradient Wn converges strongly, okay, maybe L2 log, I don't want to discuss the boundary situation, to gradient U, and gradient Zn converge strongly, that's what we proved, to 0. So gradient Un, which is the sum of those, converges strongly, locally, to gradient U. So E of Un, okay, in fact, converges to E of U. That converges to 0. So E of U is 0. And that's your minimizer. That's the end of it. Okay, so that's a good point to stop, and you can reflect on the dichotomy that I've been that I explained, that I've written somewhere here. And next time we will start discussing this general energy functional, what I can say about its infima in the case when, in the non-trivial case, when the energetical barrier exists. Okay? Thank you for your attention.
I may start with a very simple question. So in the second to last column, where you find F star.
Fx, this is for a fixed x.
No,
Yes.
the one before. So you say it's a smooth function. I cannot read. No, the column. This yes.
Function of S, smooth function of capital F.
And then the last line is this, is the
particular capital F's, which are of this form, is 0.
So this is small f then.
This is small f.
Okay.
I apologize. Of course, there's the function small f.
Okay,
Yes,
thank you.
fx. Yes, sure.
Maybe I have one less technical. What about the relation with sheets? You know that I'm most interested in sheets.
This we will discuss tomorrow.
So this is the first one of the first remark. So because so for sheets, this is you know what theorem about flexibility is related to.
So what is a thin sheet? It's omega. So here we are studying omega referential configuration, which is the general three-dimensional set. So a sheet is a particular omega, which is thin in certain direction. Okay, but it's still a three-dimensional set. So everything that I have said applies. But we will see, in fact, we will see tomorrow, right? What we can say when we know this extra geometrical property of omega, that it is thin in a certain direction. In particular, we will study, you know, by means of this gamma convergence and dimension reduction, this is what happens with the infima of E when the thickness of omega converges to 0.
If you can be more, I mean, ask a more precise question, then the flexibility theorem is, I mean, something about small scale wrinkling. I mean, I associate it to small scale wrinkling for sheets and so on. But can you have this for solids or for a bulk solid? If I take a bulk solid, am I allowed to?
This is no. So here the flexibility that I formulated today was under neglecting orientation preservation condition. Okay, so this is a non-physical condition that we will not study. I'm not going to discuss further into that. Just for completeness, I wanted to really drive this point home,
yes.
That for orientation preserving, I have rigidity in the sense we discussed. When I abandon that assumption, I have non-rigidity in the vastest sense possible, namely flexibility in the sense of the theorem. Okay? Of course, there exist many other types of flexibility theorems, but I think it's better that, you know, that we do it tomorrow. Indeed, it relates to the thin sheets and the dimension reduction, and there is a certain limiting process. So today we've just taken one fixed bulk omega. It can be thin, it can be thick, I don't care. Okay? And we discussed this general energy functional, we discussed the residual, the dichotomy, the energetical barrier, we've seen the infimum and the minimum. If it's 0, they are both equivalent. In general, it doesn't have to be the case. Tomorrow, we will look at the sort of limiting procedure that really relates to the thin sheet. Okay?
Thank you.
Yes, Ashley. That's right.
What would change
Nothing.
if it would be a subset of R2 and you try to go with the entire, so it's not a thin sheet, but just pure R2. Would anything change?
Again, if it's not.
If
So
omega was a subset of R2.
In general, this is true for everything that I said is true for any Rn. Okay, for any Rn. But this is related to, again, I stress, equidimensional isometric immersion. So you would have to think about, you know, the problem of, so you have a G, which is, say, two-dimensional metric, and think of U, which goes from R2 to R2, equidimensional. In fact, from RD to RD, same story everywhere. Okay, no relation, no. I just present it this way because we have finite amount of time, so it's good to focus on certain particular case. In particular, tomorrow we have dimension reduction, but you are completely right. So there is nothing magic about dimension 3.